Welcome to the Deep Dive. Today, we're taking a really close look at a technical paper that, honestly, it tackles one of the biggest headaches in large language models right now, the compute cost of long context.
Absolutely. It's that quadratic scaling problem.
Exactly. So our mission is to break down DeepSeek OCR, context optical compression. It's this fascinating idea about using, well, vision document images to maybe sidestep that huge token count for representing information.
Yeah, and for anyone working with LLMs at scale, you know this challenge. It's fundamental. Processing long texts just gets incredibly expensive because of how attention mechanisms work.
Like double the context, 4 times the compute. It puts a real cap on things.
It does. And DeepSeek OCR, well, it offers not just a thought experiment, but an actual system. They're kind of rethinking vision encoders, but specifically from an LLM efficiency perspective.
And the core idea they're pushing is optical compression. The hypothesis is basically if you take a big document, maybe thousands of words, render it as one image.
A high-resolution image, yeah.
All right, high res. That single image could potentially hold all that information using way fewer vision tokens than the original text tokens.
It's a radical idea, really, minimizing tokens to the extreme.
And DeepSeek OCR is the system they built to actually test this. Is it feasible?
Precisely. And the paper lays out 3 main contributions we should probably walk through.
Okay.
First, they actually quantify things. They look at the vision text token compression ratios, like how much can you compress before it breaks.
Finding that boundary.
Exactly. Second, they introduce the deep encoder architecture. And this isn't just another encoder. It's purpose-built for this task, high resolution, but crucially, low token output and low memory usage during processing.
Okay, so a specialized tool.
Very specialized. And third, they show it works in practice. They demonstrate, state-of-the-art results on OCR benchmarks, but using remarkably few vision tokens compared to others.
Okay, so let's unpack that foundational idea. Why use OCR as the test case? It seems like a smart choice.
It really is. OCR gives you this perfect setup for measuring compression and decompression. You have visual input, the compressed image, and you have a definitive ground truth output, the actual text tokens.
So you can directly compare.
Exactly. It lets you rigorously measure how much information you're keeping or losing at different compression levels. It's a clean, quantitative mapping.
So how do they measure it? There's a specific metric.
Yeah, they defined a compression ratio. They call it $6. It's pretty simple. Just the number of text tokens in the original document.
The ground truth.
Right, the ground truth text tokens, divided by the number of vision tokens the model actually uses to represent the image.
Okay, text tokens over vision tokens. Got it.
And this ratio, $6, let them empirically map out that performance boundary we mentioned. They ran initial tests on the Fox benchmark. That's a solid data set for document analysis.
And what did they find there initially?
The results were frankly quite encouraging. They found the system could maintain really high OCR precision, like 96% or even better, when the compression ratio of $6 was kept below about 10x, so in that 9x to 10x range.
Okay, so 10x compression, almost perfect reconstruction. That's already pretty significant.
It is, and what's maybe even more interesting is the robustness. If you pushed it a bit higher, say to 10x or maybe 12x compression, the accuracy stayed pretty solid, still around 90%.
Okay, so a graceful degradation initially.
Right, but then they pushed it to the limit. What happens at, say, nearly 20x compression? So imagine a document with maybe 1,300 text tokens represented by just 64 vision tokens.
That sounds incredibly compressed. What happened to accuracy?
Well, it dropped, as you'd expect, down to about 60% accuracy.
Okay, 60% isn't great for actually using the text.
No, probably not for direct use. But think about the implication. The fact that it retains any meaningful text structure at that extreme level of compression is the key takeaway.
Ah, I see. So it's not about perfect reconstruction at 20x.
Exactly. It suggests that the compressed representation, those 64 vision tokens, they still hold a surprisingly informative essence of the original document.
So even if their specific decoder, the DeepSeek 3 OE, could only pull out 60%.
Right, which is a relatively compact model itself.
It implies that a bigger, more powerful foundation model might be able to use that super compressed signal. Maybe not to reconstruct, but to, I don't know, guide retrieval or understand the gist.
Precisely. It's about signaling the content compactly. The potential is there for larger models to leverage these highly compressed forms, even if perfect reconstruction isn't the goal or even possible at that ratio.
But achieving this kind of compression, well, it needed a new approach, right? Existing vision language models, VLMs, weren't really built for this.
No, they weren't. They have different goals usually. The paper points out limitations in a few common VLM architectures when you look at them through this compression lens.
Like what?
Well, first you have the dual tower designs, like Very uses something like this. The problem there is you often need separate preprocessing for the vision and language parts,
Okay.
which makes deployment more complex, especially if you need high throughput. And it makes efficient pipeline parallelism, say during training or inference, much harder to implement.
Right, sort of a bottleneck.
Yeah. Then you have tile-based methods. InChenVL has explored this. The idea is sound break up a huge image into manageable tiles, but often the underlying vision encoder they use has a low native resolution. So to handle a high-res document, you have to create loads of small tiles.
Oh, so you end up with a huge number of vision tokens anyway.
Exactly. It kind of defeats the purpose of compression.
Yeah,
You're
right.
back to dealing with a really long sequence.
Okay, what else?
The third type is adaptive resolution encoders. Think NAVIT, which Qwen2VL uses. These are flexible, but when you apply them to documents which are often large and have fine details, like text, they can lead to absolutely massive activation memory usage in the GPUs. Anyone who's worked with high-res images knows that pain.
Oh yeah, the dreaded out-of-memory error.
Right. And they also tend to require training on extremely long sequences, which slows everything down. Pre-training, inference, pre-fill generation. It's just cumbersome.
So DeepSeek OCR was really born out of these frustrations.
Directly. The core question they set out to answer was quite practical. If you have a document with, say, roughly 1,000 words of text,
Okay.
what is the absolute minimum number of vision tokens you need to represent that visually, such that you can still decode the text successfully?
Finding that floor.
Yes. And their whole architectural design, the deep encoder, was engineered specifically to find and operate at that minimum token count.
All right, so let's get into that architecture.
Yeah.
They built the DeepSeek OCR system as this unified end-to-end VLM. It pairs their new deep encoder with the DeepSeek 3B MoE decoder.
That's right. Unified is key here. It means the whole thing, from image input to text token output, can be optimized together. It's not two separate systems bolted together.
And the deep encoder itself, that's the compression engine. How many parameters are we talking?
It's around 380 million parameters in total. Not enormous by today's standards, but significant. And its design was really driven by needing to hit all those requirements we just discussed.
Right, the high resolution, low memory, low token output.
Support for multiple resolutions, and keeping the parameter count somewhat moderate. They basically concluded no existing open source encoder ticked all those boxes simultaneously.
So they had to build their own hybrid.
Exactly. And it works in stages. There are two main components with a kind of bridge in between. The first stage is what they call the visual perception component.
Okay.
This part uses window attention. Specifically, they leverage the SAM-based architecture. That's about 80 million parameters using a patch size of 16.
Window attention. That's the key for handling high resolution without memory explosion. Right.
Precisely. Think about a 1 in 24 by 1 in 24 image with a patch size of 16 that initially generates 4096 patches or tokens.
Oh, well,
If you fed 4096 tokens into a standard global attention mechanism, the memory cost would be huge, quadratic. But because SAM-base uses local window attention here, it can process these initial high-resolution features without blowing up the GPU memory. It keeps the activation overhead manageable at this early stage.
okay, so you process locally first,
Okay.
but you still have over 4,000 tokens. You need to shrink that number drastically.
Right. That's where the bridge comes in. They call it the 16x token compressor.
16x. So it reduces the token count by a factor of 16.
Exactly. It's a relatively simple module, just a two-layer convolutional network, but its job is critical. It takes the output from the SAM component and downsamples the token sequence by 16 times.
Why use convolution here, not just like pooling?
That's a good question. Convolutional layers are really good at spatially pooling information while still learning what features to preserve. The goal isn't just to drop tokens randomly, it's to aggregate those local features from the SAM stage into a smaller set of tokens that still capture the essential layout and visual information.
So it needs to preserve where things are on the page.
Critically, simple pooling might blur important text boundaries or layout cues. Learned convolutions can be smarter about aggregating local details into a compact but still spatially informative representation. This preserved layout fidelity is crucial for the next stage.
Okay, so after the 16x compressor, what happens?
Then the much smaller set of tokens goes into the second main part, the visual knowledge component. This uses dense global attention.
Global attention now because the sequence is short.
Exactly. This part is built on the CLIP large architecture, which adds about another 300 million parameters. And since the input tokens are already processed and compressed, they actually removed the initial patch embedding layer from CLIP. It wasn't needed anymore.
Okay, so let's trace that path again for a 1024 image.
Sure. Input is 1 TIE 4 by 2024. Initial patching gives 4096 tokens. The SAM component processes these locally using window attention.
Keeping memory down.
Right. Then the 16x convolutional compressor takes those 4096 tokens and crunches them down to just 256 tokens.
4096 down to 256. Big reduction.
Huge. And only then do these 256 compressed tokens hit the expensive global attention layers of the CLIP component.
I see. So the really heavy computation, the global attention, only sees a very short sequence.
Precisely. That's how they managed to encode high-resolution visual input into a tiny token sequence while keeping the whole process computationally feasible, especially memory-wise.
Clever stating. Now what about the other side? The decoder. They used DeepSeek 3B MOE. Why MOE?
That choice was also strategic, I think. It wasn't just grabbing any available decoder. Using a mixture of experts model really highlights the potential efficiency gains here. Well, MOE models give you the power of a larger parameter count without activating all those parameters for every single token. During inference, this specific MOE model only activates, I think, 6 out of its 64 experts plus 2 shared ones.
Okay.
So the actual number of parameters doing computation at any given time is only around 570 million.
Even though the total model size is technically 3 billion.
Right. So you get the expressive capability closer to a 3B model, but with the inference speed and cost closer to a much smaller, say, 500 ever parameter model.
Okay. So it shows that the compressed visual tokens from the deep encoder are good enough for a very efficient yet powerful decoder to work with.
Exactly. It makes the whole system suitable for, domain-specific VLM research where you need good performance but can't afford massive inference costs. It proves the concept scales efficiently.
And they formalize this decoding in the paper, right? Equation 2.
They do. It basically says the decoder function, let's call it FIDE, takes the compressed latent vision tokens, $7, and reconstructs the text representation happellation. And the core idea, mathematically, is that the number of vision tokens, in $6, is designed to be significantly smaller than the number of target text tokens, NODL and HAT.
So now there's much, much less than dollars.
Orders of magnitude smaller, ideally. That equation really captures the essence of the research. Can a compact language model learn this complex mapping from a minimal visual representation back to the full text? And their results suggest yes.
So to really test the limits of this compression, finding that optimal N, they needed the model to handle different numbers of vision tokens. How did they achieve that flexibility?
They used a couple of clever tricks. One was dynamic interpolation of the positional encodings that lets the model adapt to different sequence length, and the other was defining several distinct resolution modes for processing the input images.
Okay, tell me about these modes.
They group them into native resolution modes first. These are kind of the standard ones. There's tiny at 512 by 512 input, small at 640 by 640, base at 1024 by 1024, that's the one we used in our example, and large at 1280 by 1280.
And these correspond to different output token counts after the compressor.
Exactly. After the 16x compression, tiny gives you 64 tokens, small gives 100, base gives 256, and large gives 400 tokens. These modes are the main way they evaluated those different compression ratios we talked about.
How do they handle the input image for these modes? Is it always cropped or resized?
Good point. It depends. For the smaller modes, tiny and small, they actually resize the original image down to 512 by 512 or 640 by 640.
So information is potentially lost or blurred during resizing?
Potentially, yes. Every resulting vision token represents shrunk down information. But for the larger modes, base and large, they use padding. They take the original image and pad it out to 124 by 124 or 1280 by 1280, preserving the original aspect ratio.
Padding. Okay, but then some of those 256 or 400 tokens actually correspond to empty padded areas, right? Not real content.
Precisely. And that means the raw token count is a bit misleading for the padded modes. So they had to define and calculate what they call valid vision tokens, null valid.
How does that work?
It's formalized in equation 1 in the paper. It essentially adjusts the token count based on the ratio of the original image area to the total padded area. So while large mode might technically output 400 tokens, the number of tokens representing actual image content, non-blood, might average closer to, say, 285 in their tests. It gives a fairer measure of the true compression on the actual content.
Okay, that makes sense. What about really huge documents like newspapers?
Yeah.
Even 1280 by 1280 might not be enough resolution.
Right. For those ultra-high resolution cases, they introduced dynamic resolution modes. They call them Gundam and Gundam Master.
Gundam, okay.
Yeah, it's a bit of fun naming, I guess.
Yeah.
These modes use tiling, kind of like the methods they critiqued earlier, but in a more controlled way to manage memory.
How does Gundam mode work specifically?
It's a composite approach. It breaks the very high-res image into literal smaller local tiles, processed at 640 by 640 resolution.
Okay, local views.
And it combines the tokens from those tiles with tokens from one overall global view of the image, processed at 124 by 124 resolution.
Ah, so you get both the fine detail from the tiles and the overall layout from the global view.
Exactly. The total token count is then no times 100 tokens from the 640 by 640 tiles, plus 256 tokens from the 124 by 124 global view. And no dollars can vary, typically from 2 up to 9 tiles, depending on the input size.
So it adapts, but keeps the token count per piece manageable for the memory.
Precisely. It's a way to handle things like dense newspaper pages without needing a single, impossibly large tensor.
Okay, the architecture is clever, but the data used to train this must be absolutely critical. What do they use?
Hugely critical. The data engine is really impressive. The mix was roughly 70% OCR data, 20% general vision data, and 10% text-only data. But let's focus on the OCR data. That's the core. It was split into 2 types, OCR 1.0 and OCR 2.0.
What's the difference?
OCR 1.0 was about scale and basic recognition. We're talking 30 million PDF pages.
30 million.
Yeah, massive scale. Covering about 100 languages because they wanted broad applicability, but they realized just extracting text wasn't enough for their goals.
They needed layout information too.
Exactly. So, while they had coarse annotations for many languages, they created highly detailed fine annotations for a subset 2 million pages each for Chinese and English.
What do fine annotations include?
They used sophisticated layout models, like ppdoc layout, to label the ground truth not just with the text, but with the normalized coordinates and the structural role, like paragraph, title, etc., for each text block.
Wow, so the model learns where the text is and what it represents structurally.
Yes. That spatial and structural grounding is vital if the compressed tokens are going to retain enough information for accurate reconstruction and layout understanding. They also included scene text data, about 20 million samples from sources like LEION, labeled using tools like Paddle OCR to make sure it wasn't just good at clean documents.
Okay, that's OCR 1.0. What about 2.0?
OCR 2.0 pushed into more complex parsing and structured data extraction. This is where they followed principles from JROT OCR 2.0, focusing more on understanding content within artificial or complex images, not just reading text.
Like what kind of content?
Charts, for example. They generated 10 million images of charts using tools like pie charts and matplotlib.
Okay.
And importantly, the target output wasn't just the text labels. It was the structured data represented in the chart, formatted as an HTML table.
HTML. Why HTML?
Token efficiency. Representing a table in HTML uses far fewer tokens than, say, writing it out as a JSON object or a Python dictionary structure. A very smart choice when your whole goal is token minimization.
Clever. What else was in OCR 2.0?
Chemical formulas. They took 5 million formula pairs from PubChem, rendered them as images using RDKit, and the target output was the formula in SMILES format.
Ah, the standard machine-readable chemical string format, so it learns to translate the image directly to SMILES.
Exactly. And finally, they included about 1 million samples for plane geometry, generated using something called slow perception. The idea was to encode simple geometric figures like line segments along with their coordinates.
That sounds tricky. Geometry depends so much on precise relationships.
It is tricky. They note it's challenging because compression inherently wants to discard some of that fine-grained spatial detail that defines geometric shapes. It really tests the fidelity limits.
Okay, massive and diverse data set. How do they actually train the model with all this?
They used a two-stage approach. Pretty straightforward conceptually, but computationally intensive.
Stage 1.
Stage 1 was just training the deep encoder by itself. They fed it all the OCR 1.0 and 2.0 data, plus about 100 million general vision samples, and trained it for 2 epochs. This built the core visual understanding and compression capability.
So, encoder first, then stage 2.
Stage 2 brought the whole system together. The pre-trained deep encoder plus the DeepSeek 3B MoE decoder. Because this is a large multi-component model, they had to use pipeline parallelism, PP, to train it effectively.
Splitting the model across GPUs or nodes?
Yes, across 4 pipeline stages. And how they split it is interesting.
How so?
PP stage 0 contained the first part of the encoder, the SAM base component, and that 16x compressor. And importantly, these were frozen in stage 2.
Frozen, so their weights didn't change.
Correct. They locked down that initial visual perception part. PP stage 1 had the second part of the encoder, the CLIP component. This was unfrozen, so it continued to learn and adapt its representations based on feedback from the decoder.
Ah, okay. So the global visual knowledge part kept learning.
Right. And then the MoE decoder layers themselves were split across PP stages 2 and 3.
And this whole setup ran on quite a bit of hardware.
Oh, yeah. They used 20 nodes, each with 8 NVIDIA A100 GPUs, the 40GB version. With data parallelism across these, they achieved a large global batch size of 6 Winotter. It demonstrates that while complex, this kind of training is feasible at scale.
All right, let's get to the results. How well did this compression actually work? They looked at the Fox benchmark again, right? Table 2 in the paper.
They did. They focused on a subset of English documents from Fox, specifically pages with text token counts ranging from about 600 up to 1,300 tokens. This gave them a good spread to test the compression limits.
And what did that boundary analysis show? What was the near lossless point?
It really confirmed those initial findings. For the documents on the lower end, say 600, 700 text tokens, they achieved 96.5% precision using the tiny mode, 64 vision tokens. That's a compression ratio of about 10.5x.
10.5x with 96.5% precision. Pretty good.
Very good. And if they bumped up slightly to the small mode, 100 vision tokens, the precision went even higher to 98.5% with a compression ratio of about 6.7x.
So it clearly shows that for reasonably sized documents, you can get 10x compression with minimal loss.
Absolutely. That seems to be the sweet spot for high fidelity.
But what happens when you have longer documents and you try to maintain that high compression, say, the 1,200, 1,300 token documents?
That's where the limits start to show, especially at the most extreme compression. For those longer documents, using the tiny mode, 64 tokens, resulted in that nearly 20x compression ratio.
Yeah.
And the precision dropped significantly, down to 59.1%.
Okay, so 20x is definitely lossy for longer text.
Definitely. However, if they just increase the vision token budget slightly to 100 tokens using the small mode, the compression ratio is still high, around 12.6x, but the precision jumped back up to a much more usable 87.1%.
So that range between 10x and maybe 13x seems critical. Performance drops off more steeply after that.
It seems so, and we need to think about why it drops off past 10x or 12x. The authors suggest 2 related reasons.
Okay.
One is simply that longer documents might have more complex layouts, making the spatial reconstruction harder.
Makes sense.
But perhaps more fundamentally, especially for the 64 token case, the degradation likely comes from the sheer loss of visual detail. Remember, to get 64 tokens, they had to resize the input image down to 512 by 512.
Ah, so things get blurry, details get lost.
Exactly. High-frequency details just disappear. And the authors make this interesting connection. They suggest this degradation is analogous to a kind of forgetting mechanism. As visual fidelity decreases due to lower resolution, information is progressively lost.
So the takeaway for practical use is aim for 10x if you need near-perfect results, maybe push to 12x if you can tolerate slightly lower accuracy. But beyond that, expect significant degradation.
That seems to be the operational guidance from this study, yeah. It directly informs which resolution mode you choose based on your accuracy needs and typical document length.
Okay, that covers the compression boundary. What about overall performance against other state-of-the-art OCR models? They use the on-the-dock bench for that.
Yes, Table 3. They compared DeepSeek OCR against other leading end-to-end models using edit distance, or ED, as the main metric. Lower ED means better performance.
And how did DeepSeek OCR stack up, especially considering its focus on token efficiency?
It stacked up extremely well. Let's look at token counts versus performance. DeepSeek OCR using the small mode, remember, that's just 100 vision tokens,
Yeah.
achieved an overall edit distance of 0.221. That was actually better than a model called GOT-OCR 2.00, which needed 256 tokens to get an ED of 0.287.
So less than half the tokens, but better accuracy.
Precisely. A 2.5x reduction in tokens led to a cleaner output. That's a strong win for efficiency.
What about the high-resolution modes like Gundam?
The comparison there is even more stark. DeepSeek OCR in Gundam mode used, on average, fewer than 800 tokens per page.
Okay.
And it achieved an overall ED of 0.127. Now compare that to another strong model, Minor U 2.0. To get a slightly worse ED of 0.133, Minor U 2.0 required almost 7,000 vision tokens per page.
7,000 tokens versus less than 800.
Yeah. It's nearly an order of magnitude difference in token count for comparable or even slightly better performance from DeepSeek OCR.
Wow. Okay, so that really drives home their main point. State-of-the-art results are possible with dramatically fewer vision tokens using their architecture.
Exactly. Token minimization here didn't require sacrificing performance. In some cases, they even improved it while using far fewer tokens.
Do they break down performance by document type? Does the optimal mode change?
Yes, Table 4 looks at that. It confirms the intuition we discussed. For easier, less dense document types, things like slides, books, reports, the tiny 64 tokens or small 100 tokens modes often perform very well.
And why is that?
Mostly because those document types tend to have fewer text tokens to begin with, maybe under 1,000. So even with 64 or 100 vision tokens, the compression ratio naturally stays below that critical 10 by 12x threshold.
Got it. But for the really challenging stuff.
Right. For dense documents like newspapers or multi-column academic papers, which can easily have 4,000 or 5,000 text tokens.
Yeah.
Trying to compress those down to 100 or even 256 vision tokens would push the ratio way too high, leading to poor results. For those, you need the lower compression ratios offered by the Gundam or Gundam Master modes to maintain fidelity.
So the choice of resolution mode is really about managing that compression ratio based on the expected text density of the document.
Exactly. These results provide a really practical guide for how to apply the model effectively depending on the task.
Okay, the numbers look good. But the paper also talks about more qualitative capabilities, like something they call deep parsing. What's that about?
Yeah, deep parsing comes from the combination of the model having learned detailed layout information from those fine annotations and the complex OCR 2.0 tasks it was trained on. It basically means the model can do more than just read text. It can understand and extract structured information from images embedded within the document, all using the same unified prompt.
So it's not just OCRing the main text, but analyzing figures and tables too.
Exactly. It becomes more of a document intelligence system. For example, they show it analyzing a chart image found within a financial report. And instead of just pulling out axis labels, it extracts the actual data points and outputs them directly into that token-efficient HTML table format we discussed.
So the output is immediately usable for analysis or database entry.
Right. It's transforming the visual information into structured data, not just text.
What other examples of deep parsing did they show?
They showed it working on chemical formulas. If it sees an image of a chemical structure in a document, it can recognize it and translate it directly into the SMILE string format. Again, turning visual domain-specific information into a standard machine-readable format. That could be huge for scientific literature processing.
Definitely. Integrating visual recognition with domain knowledge?
They also showed it generating dense captions for natural images found within documents or identifying objects in them based on the prompt. This demonstrates that the underlying visual grounding is still there, even though the encoder is optimized for compression.
So it retains general VLM capabilities.
It seems so, yeah. It can still see and describe regular images if prompted correctly.
What about that plane geometry task? You mentioned it was challenging.
It is. They show the model attempting to copy or describe simple geometric figures. And while it can make some progress, they acknowledge it's difficult.
Why is geometry so hard for this approach?
Because geometric figures rely on very precise spatial relationships between points and lines, high compression ratios, which involve downsampling and potential blurring.
Can easily distort those precise relationships.
Exactly. It really highlights the trade-offs inherent in lossy visual compression. You gain token efficiency, but you might lose the ultra-fine-grained spatial fidelity needed for tasks like precise geometry reconstruction. It shows where the current boundaries are.
Okay. Another crucial aspect for real-world documents is language. Did they address multilingual capabilities?
Yes, absolutely. Given that their OCR 1.08 data included 30 million PDFs crawled from the web in about 100 languages, multilingual OCR was a must-have.
So it can handle languages other than English and Chinese.
Oh, yes. They specifically show examples of it working on languages with complex scripts, like Arabic and Sinhala. It's trained for broad language coverage.
And can it handle different output needs, like with or without layout?
Yes, that's important too. Depending on the prompt, it can generate the text output preserving the layout structure using coordinates or other markers, or it can just output the raw text content without layout information.
That flexibility is key for practical data processing pipelines.
For sure. When you're processing millions of diverse PDFs, you need that adaptability. It makes the model a much more viable tool for large-scale data production.
And just to confirm, despite the OCR focus, it didn't completely lose its general vision skills.
Right. They include examples, figure 12, showing it can still do basic image description, object detection, visual grounding, etc. The inclusion of that 20% general vision data during stage 1 training seems to have preserved those core VLM functionalities.
So future researchers could potentially build on this compressed representation for other tasks, too.
That seems to be the hope. While the paper focuses heavily on OCR and compression as the primary use case and proof point, they've kept the general vision interface intact, suggesting the underlying efficient encoding might be useful more broadly.
Okay, let's pull back and think about the bigger picture. The core finding seems solid. You can get roughly 10x text-to-vision token compression for documents with near-lossless OCR quality.
Yes, that's the key quantitative result.
And even at 20x compression, while accuracy drops, it doesn't go to zero. It retains significant informational relevance.
Correct. Around 60% accuracy, which, as we discussed, is more significant for what it implies about the compressed representation than for direct usability.
So what does this mean for the huge challenge of ultra-long context in LLMs, that quadratic scaling problem we started with?
This is where the paper gets really thought-provoking. The authors draw this powerful analogy, shown in their figure 13, between this idea of contexts, optical compression, and how human memory seems to work, particularly regarding decay or forgetting.
Human memory decay. How does that connect?
Well, think about your own memories. Recent events are usually sharp, detailed. But memories from further back, they tend to get fuzzier, right?
Yeah.
Less detailed. Maybe you only remember the key points, the gist.
Yeah, that makes sense. Details fade over time.
Right. There's a progressive loss of detail. The authors compare this temporal decay in memory to the spatial degradation of visual perception. Things far away are blurrier, less distinct than things close up, or, in their case, images rendered at low resolution are blurrier than high resolution ones.
Okay, so time decay in memory is like spatial or resolution decay in vision. How do they apply that to LLM context?
The idea is to treat the LLM's context window, especially its history, using this principle. Instead of storing all past conversation turns or document sections as full-fidelity text tokens, which gets quadratically expensive, you first render that historical text into an image to get an initial optical compression.
Okay, like using DeepSeek OCR's method.
Yes, but then as that piece of context gets older, further back in the dialogue history or document, you progressively downsize or recompress the rendered image representing it.
Ah, so you apply more compression to older information.
Exactly. It mirrors memory decay. The most recent context might be stored at, say, 10x compression, high fidelity, higher token cost. Context from a bit further back might get compressed to 15x, slightly less detail, fewer tokens, and very old context might be stored at 20x or even higher compression. Just the gist, very few tokens.
So you create this multi-level compression hierarchy within the context window itself.
Precisely. You're dynamically balancing the need for fidelity against the computational cost based on the age or assumed relevance of the information. Recent stuff stays sharp, old stuff fades gracefully but doesn't disappear entirely.
And the LLM's attention mechanism would then operate on these differently compressed visual tokens.
That's the theoretical proposal. Attention wouldn't work on the full, massive text sequence. It would work on this sequence of latent vision tokens, where the level of detail available for any given pass turn is a function of how far back it is.
That sounds potentially revolutionary for breaking the quadratic barrier. It suggests context size could theoretically be unlimited, just with varying fidelity.
That's the promise, yes. It shifts the problem from a hard limit on sequence length to a more nuanced management of information fidelity versus computational resources.
Now, let me push back slightly here, playing devil's advocate for our audience. This works well for OCR data, text laid out on a 2D page. Does rendering, say, conversational dialogue history into an image give you the same stable spatial structure to compress effectively?
That is an excellent question, and it's the critical research gap the authors acknowledge. The optical part of the compression definitely relies on the 2D spatial layout. Dialogue doesn't have that same inherent structure.
So the compression ratio might not be as good for unstructured text.
It might be lower, yes. We don't know yet. However, the fundamental principle still holds some advantage. Even if the ratio is less than 10x for dialogue, rendering a very long text sequence into any compressed visual format where the number of vision tokens is largely independent of the original word count.
Still breaks the direct link between text length and token sequence length.
Exactly. It decouples the token count from the raw text length, which is the key to overcoming that n-squared scaling of attention. So even if less efficient than for documents, the structural benefit of moving from a 1D text sequence to a 2D or latent visual representation could still be significant.
So the ultimate theoretical promise here is a new kind of LLM architecture where the context isn't a fixed bottleneck, but a dynamic, compressed space managed over time.
That's the exciting possibility this research opens up, a potential path towards truly scalable, perhaps even unbounded, context windows. Hashtag outro.
Okay, so wrapping up this deep dive, DeepSeek OCR really seems to play two roles. On one hand, it's fundamental research giving us hard numbers on context optical compression limits.
Yes, mapping out those boundaries is crucial work.
And on the other hand, it's apparently a very practical tool right now. They mentioned it can produce high-quality pre-training data, OCRing documents, with layout info at a pretty staggering rate.
Yeah, the figure they quote is over 200,000 pages per day processed on a single A100 GPU. That's production scale. So it's both a research vehicle and a workhorse tool.
What do the authors see as the next steps to really prove this concept for general LLMs beyond OCR?
They're quite clear about that. Future work needs to move into what they call digital optical text interleaved pre-training. So training models on a mix of regular text tokens and these compressed optical tokens.
Testing if the model can fluidly switch between them.
Exactly. And crucially, they need to perform rigorous needle-in-a-haystack evaluations.
The standard test for long context recall. Can the model find a specific piece of information buried deep within a massive compressed context?
Precisely. That's the ultimate test. Can the language model effectively decompress and retrieve the necessary information from these highly compressed visual representations when prompted? Passing those tests would be the real validation for this architectural shift.
Okay, so here's a final thought to leave our listeners with. We've seen solid evidence for near-lossless 10x compression in the OCR domain, and this compelling, if speculative, analogy to human memory. If optical compression in some form becomes a necessary component for truly massive context, how might that fundamentally change how we design LLM architectures from the ground up? Could we really be moving towards models with genuinely unbounded, dynamically managed context?
That's the multi-billion-dollar question, isn't it? DeepSeek OCR has certainly laid down a fascinating and challenging path for the community to explore.